Let me quickly review your opinion. Or why do you think? What is your answer?
uh, to do everything at the same time, basically while training it, your data set would explode because you would need every combination of the first task with the second task, every combination of the first task with the third task. So training it would be computationally inefficient.
Oh, it's a very interesting. Actually, okay. And Yongtak?
When you training the machine, we use some kinds of probability models, something like that. And it specific to the fit, it fit to the specific data. And when you call the problems called general problems, we have to broaden data, right? So there are so many data, and there are no relationship between there. So we can calculate the models to fit the data.
Okay. Sanas?
So, because of the vast variety of the types of data, we also suppose AI is trained on multiple tasks. There also comes the question where it has to recognize what kind of an input it is. So we need to have a separate layer which first processes what kind of an input it is, and only then we can go further of choosing which model we are going to use
Okay.
to evaluate the input.
Okay. Input or model to choose which model we use. Yeah. Right. Saros?
Yeah, I mean basically like one model will be trained for a specific task. So the parameters for that model is aligned to like, to do something for that particular task. So if you want to do multiple tasks, so some parameters may not match with that general thing. So the other thing that he mentioned, if we want to do multitask, there needs to be something else. We can have multiple models doing multiple tasks, and then we can have something which can decide based on the input which model it has to invoke to perform the task.
Okay. And Pascal?
In this, in the machine learning scenario, the most important part I come up with data. So all three tasks has a three different kind of data sets. So if you want to do all tasks at one time, so you need to mix the data set all together, which will not generate anything good because we will lose the uniqueness of each data. So mixing all together and performing all tasks at one time, we will not able to achieve at all. So
Okay.
yeah.
Sanjay? Hello, we have a guest from other lab. Yeah, he is interested in the general AI stuff. So, Sanjay, your opinion?
So, whenever we try to do multitasking, there are so many combinations of decisions to be made. So at any given instance, like trying to combine all the decisions at a given instance is hard as well.
Okay, so combining decisions. Okay, so I think you guys have in general very interesting answer. So my idea is also similar to Paul or Youngtak's idea and Pascal's idea. So let's say we have some model. So we should think in terms of the inputs and outputs. So let's say there is an input which receives a video. So let's say it receives a 100 by 100 video. So there will be 10,000 inputs for each pixel. And let's say it also receives some audio. So to make it simple, it receives let's say 10 millisecond interval of let's say 1 second. So there will be 100 inputs for the audio. And if we think about, if we build a model that does these three things, self-driving, machine translation, and image generation, let's say to make a very simple model, there is a 4 output, which is like left, right, XL or stop. This is for driving. And there are, let's say, for motion translation, let's say there is a 24 outputs, which basically say outputs A, B, C, D, E, F, things like that. And for audio, let's say for now, this is an image generation. So to generate 10 by 10 image, we should have 100 outputs for image generation task. So let's say if we think about this way, we have a training data for self-driving. So self-driving data, to make it simple, let's say it has a video camera input and it outputs 4 actions, so like left, right, accel, stop. So the data set for the self-driving car only contains this part, right? And to train this, let's say, whatever neural net, for this input, we don't have output for this kind, right? If we are trying to use a supervised learning scheme, we need some kind of ground truth data for these outputs too. So that's basically my explanation for why multitasking is so difficult. So the training data for self-driving also requires output for the machine translation and image generation. And the same goes with the machine translation and image generation. So I call this exponential data hypothesis. This is a hypothesis, by the way. I might be wrong. So the required data for multitask n, let's say there is n task, is multiplicative, not additive. So we cannot just add the data. We somehow have to have every combination of the data. So that's my basic intuition behind why multitask learning is so difficult. So this is also my prediction based on this observation. Nowadays, deep learning is so hot, but in my opinion, while deep learning is a very good function approximator, our current approach is not scalable for artificial general intelligence due to the exponential data hypothesis. So anyone in this room understand what is a function approximator is? Sanjay, do you understand what is a function approximator?
You don't know the real value, but you try to approximate.
Yeah, let's say we have some function. Think in terms of the function. In terms of the, let's say there is a function that receives an image and generates a, how I say, driving action, right? We humans, let's say if we show the how I say, sequence of image, and then we can generate actions naturally, right? Mm-hmm. And there is a very complex. If in the image there is a traffic signal, we should stop, things like that. So if we think this as a function, then this function is really complex, right? Mm-hmm. So it is not as easy like y equals ax plus b. There are many if image contains traffic signal, stop, or things like that, which if we think in terms of the pixel level, then it becomes like if a pixel is red and the next pixel is red and this one is red. If there is a 4 red and there is a black and black, then we should stop, right? And by the way, this traffic light can be large or small, or rotated, things like that. So this function is really crazy, but we can think this is just a complex function that is shown on the input space. And deep learning is, in essence, you can think it as a function approximator. And by function approximator, I mean there are some mathematical work to prove that neural net is a universal function approximator, but it works somehow as a very basic intuition like this. So each neuron somehow captures the essence in this small segment, and by adding lots of neurons, we can basically imitate behavior of lots of functions. So let's say if for imitating y equals ax plus b, the neural net way might be for this input, assign this output, for this input, assign this output, things like that. So this is how neural net approximates a complex function. And I said this approach is not scalable for artificial general intelligence because due to the exponential data hypothesis. But there are some details. What I mean by the deep learning is deep learning as it is now, and things are changing rapidly. So we will go when we are actually implementing some artificial general intelligence model. We will probably use a dense representation and sparse representation. By dense, what I mean is, let's say you have a 100-dimensional dense vector, then everything has a value like a 0 point floating value, right? As in word embedding. And for sparse vector, if there is a 100-dimensional sparse vector, let's say sparse and binary vector, out of 100, let's say only 2 or 3 bit is 1, the remaining is 0, right? So I think intelligence can be built many different ways, and we can still use the dense representation as a deep learning. So, and there is another approach in sparse representation. This will come later. So what I saying this is you should think this as a more of the application specific deep learning which you guys can see nowadays. So
One question, Professor. So here we are trying to train one model to do multitasking?
you can think that way, yeah. Yeah. Mm-hmm.
For this problem, what we have talked about, like multitasking problem.
Mm-hmm.
Multitasking is like not possible right now, or it is not very good. But to solve that issue, we can also try to get for the concurrent task, where the system has these 3 tasks as independent, but they are switching so fastly, so end user will not able to recognize it. So actually internally it is concurrent task, but for the person it seems like a multitasking.
That's so this is my hypothesis. So I think you can I might be wrong, and there can be many different way of building intelligent machine. So it's like once we found how we can build the theory of aerodynamics, actually building plane or machines that can fly, you can build a plane, fixed wing or jet wing or helicopter, or nowadays researchers are making flapping wings too, right? So having said that, so I might be wrong, but for your rapidly how I say multitasking
It's a concurrent task, not a multitasking.
Yeah.
At one time he is doing one task, but there are task switching happens where they don't for a right statement.
So
they don't use the resources.
So my counter argument, this is a quick counter argument, so I might be wrong. So if you think this model, right? So there is a machine translation model, right? But let's say there is a image captioning model,
Yeah.
right? So there is an image captioning model. So both machine translation and image captioning wants to use this text to output,
Yeah.
right? And your concurrent multitasking machine has generated two output. One is alphabet in Hindi. I don't know Hindi, but Hindi, and one is image captioning. So based on the image, it generates this textual description. So you have a two candidate for the current output, right? And let's say you have n candidate for current output module. Then deciding at this time I'll use output from this module. At this time I'll use output from this module. Becomes actually very difficult problem that requires humans understanding of the things like a context. If it is this context, I need to use this output, things like that, right? And this, the context model, which given n candidate, select one actual action output. This is the devil in the detail that makes your concurrent multitasking machine very difficult. This idea is similar with Sanas or Saroj's combining decision. Is it this combining decision? Yeah, so Sanjay's argument. So this is the where it becomes difficult, right? So, but this is more of the philosophical discussion. So there is no right or wrong answer. So you are free to pursue your direction. And when you have more idea, you can come to me. So now let's go to the. Now we did there with the history or what we want to achieve. So let's go slightly deeper. We want to build something, right? We do not want some philosophical discussion. So let's say we build a thinking machine. This is a thinking machine. It has you can think of the robot on the wheel. It has a video camera and it has a speaker and mic, things like that. So it receives it goes around this room on a wheel and it receives a video and sound input. And let's say this machine generates a thinking as an output, as humans do, because this is a thinking machine. It does not do anything, it just think. So if there is a pizza here, it will be go to the pizza and see, say like, there is here are a lot of people in the room, where is my pizza? Or you think of the pizza, oh, there is a pizza, and where maybe the next thing will be happy face. So after eating pizza, I'll be happy, things like that. So if we want to build a thinking machine, here is my second question. First question was this, why multitasking is difficult. Now my second question is, what should be the output format? Because we are computer programmers, we have to generate thinking as something, and it can generate a text output, or it can generate a movie output, image output, image sequence output, right? So what should this machine generate? That is my second question.
Simplest would be the text.
Pardon me?
Simplest form of output would be the text.
Okay.
It says the thoughts out.
Okay.
So that can be read and then interpreted in a single way.
So
but if
yeah, Sana's text and Saros,
I also said that.
yeah, text.
So thinking output in which sense? Like the individuals should able to understand better way.
So let's say if you are driving and you are hungry, do you have this experience like imagining
Eating.
burger or pizza or curry or something, not thinking about I need some hamburger, things like that. You just imagine a burger. things like that. So that's what I mean by this sequence of image.
Okay. So no, my question was: is this module is generating output for someone else or for them, for himself?
For now, I think let's say it for himself.
Okay.
Mm-hmm.
Because that will impact the output.
Yeah,
Will be
yeah.
able to understand someone else.
Yeah. That's a good point. Yeah. So what is your choice?
If they are generating for themselves, then text would be good.
Text, okay. And Sanjay? Image. And Paul?
Both.
Both.
Because-
That's a good answer. Can you elaborate? Do you have something to say?
Different people would think
Mhm.
differently.
Mhm.
So some people would imagine and some people would just
Mm-hmm.
have the thought.
Okay. That's a good. And Yongta?
Instead of the context.
Oh,
I mean, it's the
depends on the context.
The result will be the set of the context.
Set of context. So it's not text. It's not
Not
image.
text and not image.
Let's say it's a vector, and this vector can be, if it goes to the image decoder, it generates an image.
Yeah.
If this vector goes to the text generator, then it generates a word.
Yeah.
So it generates simply a conceptual vector.
Yeah.
Right?
And usually people think the
Concept.
okay, I'm hungry,
Mm-hmm.
and then is the hungry is the context, one of the contexts, and the next time is what I will eat.
Mm-hmm.
And eat is the context.
Mm-hmm.
And the next is I will eat the pizza.
Mm-hmm.
Eat and pizza is the context of the day.
Mhm.
So how do you think of it?
Yeah, so it will generate like a sequence of
Yeah,
vectors. Yeah. And what was your name?
Sadik.
Sadiq?
Sadik, yes.
Sadiq. Can you quickly introduce yourself to people in this room?
Yeah, I'm Sadik. I'm doing PhD. I've been doing PhD with Dr. Lee. Yeah, I'm also trying to collaborate with this professor to see if I can find a good match.
Mm-hmm. Okay, so how do you write?
Shadek.
Shadek. Sadiq.
Yeah, so I'm thinking that the robot will first think of objects.
Uh-huh.
Like, different for kids. So then later machine uses text to identify the context that he said. That means by using objects, he will define a context.
Mm-hmm. Yeah, so object depending on the context. Okay, so this was actually a trick question. My question actually was, what do you guys use when you guys think, right? So I was not asking about the thinking machine, I was thinking about yourself, and there are many people are different. Most of people mixes together. So depending on the context, if I have to think about the sequence of event, like what happened today, then it happens in the textual form. If you have to have some impulsive thinking, like seeing a beautiful woman, that kind of impulsive thinking comes with visual thinking. And there are verbal thinking, which is mainly comes in a textual format, language format. So that's like when you are reading books. So reading books is very close to following verbal thinkers' thinking. And there is also very interesting people who thinks only in image. And my, biggest mistake was that I was thinking thinking is a language. That is my mistake. So I thought thinking is by language, or language is the medium of the thinking. So that was my mistake. And while I go deeper and deeper to solve the text problem, I realized that I cannot solve text problem by studying only text, right? So let me introduce one visual thinkers. So this is Temple Grandin. She is an animal scientist and she is autistic. Do you know, guys, know what is autism?
Yeah. It's like disability.
Physical disability.
No, not physical
They are not able to
Learning
communicate
disability.
socially. Yeah. They are
Pardon me?
not able to communicate
a
socially
learn-
with the other people.
Yeah, so autism is actually very broad spectrum. Generally, they have a difficulty in communicating. And it is a very broad spectrum. So you guys need to study on Wikipedia. And so, what is nice thing about her is she has a very good memory, visual memory. So photographic memory. So this is the plant she designed. By the way, she designed like about 70% of the all meat packing factories in the United States. So, and she memorizes her drawing in her head, every drawing she made, and she says, and she wrote a book, Thinking in Pictures. So this is an interesting book I highly recommend. And let's see.
So what is thinking in pictures? It's literally movies in your head. My mind works like Google for images. Now, when I was a young kid, I didn't know my thinking was different. I thought everybody thought in pictures. And then when I did my book, Thinking in Pictures, I started interviewing people about how they think. And I was shocked to find out that my thinking was quite different. Like if I say, think about a church steeple, most people get this sort of generalized, generic one. Now, maybe that's not true in this room, but it's going to be true in a whole lot of different places. I see only specific pictures. They flash up into my memory just like Google for pictures. And in the movie, they've got a great scene in there where the word shoe is said and a whole bunch of 50s and 60s shoes pop into my imagination. Okay, there's my childhood church, that's specific. There's some more, Fort Collins. Okay, how about famous ones? And they just kind of come up kind of like this, just really quickly, like Google for pictures. And they come up one at a time, and then I can think, well, okay, well, maybe we can have snow, or we can have a thunderstorm. I can hold it there and turn them into videos. Now, visual thinking was a tremendous asset in my work designing cattle handling facilities. And I've worked really hard on improving how cattle are treated at the slaughter plant. I'm not going to go into any gucky slaughter slides. I've got that stuff up on YouTube if you want to look at it. But one of the things that I was able to do in my design work is I could actually test run a piece of equipment in my mind, just like a virtual reality computer system.
So I also recommend you guys to watch her TED Talk. It's quite fascinating. So that was what she said. So it's very difficult to know that your way of thinking is different from others because it's difficult to see how others understand things. But for her, it was the moment. So how many people in this room, when I say something like shoe, then you have some kind of very general abstract hand-drawn like image of the shoe, general shoe. Yeah. And probably most of us will have this very general image of the shoe. But for her, it's like a Google search. If you search, do a Google image search of the shoe, then every shoe is very specific, right? And this is the drawing drawn by the people, a child by age of 9, and you can see he has a very not strange, but very accurate sense of the dimensions. And this thing is interesting. So this old lady, around 60, didn't draw anything, but by 60 she had some accident, so she had to do a brain surgery. She lost ability to speak, and then since then she started to draw very photorealistic drawings. This was reported in 1998 Neurology Journal. So, one way we can explain this.
The short-term memory is what is happening right now.
Uh-huh.
Like the moment after moment will
Mhm.
temporarily be registered in your brain.
Yeah, yeah.
And
So, yeah.
it gets converted to long-term memory when you give it some time. When it goes from active thinking to diffuse thinking,
Mhm.
it has to sink into your brain.
Oh yeah.
When
So working memory is like your computer science way of expressing it is it might be your RAM or cache, and long-term memory might be your hard disk. So to do anything in your brain, you first load the context in your brain. So now I am speaking, but as Young-tak said, there is some context to it. Like I am hungry, I want to eat something, there is a burger, things like that. Or I need to do presentation, then I need to open the laptop and start the PowerPoint, open the file, things like that. So these kind of things are very small in human, very precious resources. So that's where this working memory is similar to the short-term memory. And how the psychologists found this? So they asked people to do one thing, and people can do relatively well. And if you ask one people to do two things at the same time, their performance degrades very badly, like 10%. Let's assume the performance of the person for single test was 100%, right? We expect like a 50 by 50 performance, but it does not. It goes like actually 10% to 10%. As a computer scientist, we can explain this as a context exchanging cost.
deadlock.
Not deadlock. This is more of the context switching cost. Yeah. So to load something, you have to unload. Yeah. Right. So that is actually, if it happens very frequently, it's very costly. And that was how LSTM came. Is from the theory of working memory, and this Bedley's model of working memory came later. It's a second revision of this theory of working memory. That what Bedley found was that if you ask people to do two things at the same time, sometimes their performance does not degrade at all, right? So if I ask you drive while speaking on a phone, your performance does not degrade that much. But if I ask you drive while you are doing text, your performance degrades a lot, right? So what he found was that there are actually two separate working memory. He called it visual spatial sketchpad and phonological loop. So this visual spatial sketchpad is what stores some visual images, and phonological loop is storing some auditory input. And this thing is actually interesting. Do you guys, when you read books, if you read some text, do you hear your voice in your mind?
Yes.
Yeah, we call inner voice. So this phonological loop is responsible for generating this inner voice. And if I say, my phone number is 765-426-7448, you guys are able to capture like 1 second to 2 seconds of memory as it is. So it can store like 1 to 2 seconds of the audio recording. So my hypothesis is that if there is a problem in autism, sensory if there is a problem in developing phonological loop, they somehow strengthen this route to how I say replace or augment the working. So this creates the phenomenon of the photographic memory and rigid thinking. So let's go one step. So why language is difficult for autistic people? So Saroj said autistic people has a difficulty in communicating. So we can think language acquisition is co-occurrence of sensory input about object and the accompanying vowel sound. So it's like when you were a baby, your mom say, "Hello, I'm your mom," and the image of mom and the sound of mom occurs frequently together. That's the co-occurrence. So it's like Pavlov's dog experiment. When you hear the bell, the dog expects some food. Yeah. However, this is the everybody knows Pavlov's dog experiment, right? Sanjay, do you know? Yeah. So, however, for autistic people, they have some sensory problem. So, people's voice sounds like a thunderstorm. It's too painful, too loud, or sometimes sounds like a broken mobile phone. There is lots of noise and you cannot understand what people are saying. So that is when the autistic people blast their head. So because the sound is too painful, they cannot attend to the sound input. So they have a hard time developing this language. So I'll skip this part. And this is the, if you know a little bit about the autism, autistic people are famous for their rigid thinking. So you guys can read this. This was to give you an idea about what is rigid thinking. This was supposed to be fun. I'm not sure if it is. Okay, Paul, do you got the idea? Yeah. So this is one movie at the Rain Man. That was a very famous movie, old movie. So here Dustin Hoffman is autistic people, and he is crossing the road, and the traffic sign says changes from walk to don't walk. So he stops there because the sign says don't walk. So why language rigid thinking? So I'm sorry guys to bring the autism. This is we had a detour of the topic, but the reason why I brought the autism was to talk about this. Do you guys think animals think?
Yeah.
Who think animals don't think? Nobody, right? So there is a thinking, animal thinking, right? And there is a human thinking. And if we think about language, animal think without language, right? And then we human sometimes use the language to think. So there is a thinking with the language. And my hypothesis that I brought this was that there is a autistic thinking that can be a bridge between the animal thinking and human thinking. So by studying their characteristics, we can get some basic intuition behind the animalistic thinking. So now this is actually the beginning of the real talk. This is, so far it was more of the background. This is the level of abstraction. This is a very famous diagram from the MAR. So if you type Mars level of abstraction, this is what you get. So what this diagram is saying is that to describe the working of the intelligent systems, you can have a multiple level of way of describing what is happening there, right? And because we are computer scientists, the device you can think as a transistor, right? So to describe what is happening in your laptop, we can start from the transistor. And this will be very painful and very detailed way of describing something. And there is a operator. So by operator is you can think of this as more of the machine code, machine binary code. So I don't know if you have experience writing assembly code. So you can think this in assembly code. There are types of operator that is available, like if jump, if not jump, or add, things like that. There are some operations. So you can describe it in terms of the operator. And there is an algorithm. So algorithm describe, the algorithm. And there is a theory. Theory might be Turing's universal Turing machine. And if we develop AI, we will probably can describe things in these 4 different level of layers. And the device for the human intelligence might be things like human neural cell, right? And we somehow know a little bit about the operator. And I will explain the theory and algorithm in this talk. However, one thing I would like to comment is the operator here should be only algebraic operator. What is algebraic operator? Algebraic operator is like a plus, minus, multiply, divide. No logical operator is allowed because logical operator creates a problem. So you can think the old AI, like if traffic signal is red, cross, they failed because they used the logical operator. And this logical operator was, devil in the detail that broke their work. So this is the theory. This is my theory, meaning that it can be wrong, and you guys are free to think about it. So thinking is a random walk in a probabilistic knowledge graph conditioned on the context. Context can be previous nodes, sensory input, or motivation. And let's see. What do I mean by the probabilistic knowledge graph? So it's a graph like this, and each node is a concept like a ball, or throw, sphere, play, and every node has an associated probability. So if it is a ball, it has a high probability of association with a throw or sphere than something like a car or airplane or things like that. So it has a very weak connection. So you can thinking is a random walk in this. For each node, it samples where to jump next based on the probability. And this node can be a word like a ball or concept like a ball, or it can be a sensory input like an actual image of the ball. So if we think about the cow, right? Let's say if a cow was hit by a cowboy with a black hat, then after that accident happened, this cow, whenever it sees a cowboy with a black hat or a person, any person with a black hat, it fears and it tries to run away, right? So it associates the image of the black hat with the pain or fear. There is a high probability of jumping to next. So this node can be also action, like if the next node is a throw action node, then it will actually do the action. So if we think about this node probability, then the problem is it depends on the context. Let's say if we represent context as a previous node, if we are talking about the apple pie or at the dinner table, then the word apple is related to actual fruit apple or banana, right? There is a high probability with this, but low probability with MacBook Pro or Google. However, if we are talking about latest iPhone, the word apple has a high probability with MacBook Pro or Google. So the actual probability changes depends on the previous node, right? So if we now go back and see this is what I mean, right? If there is an N concept, like everything Sanjay knows, like ball, bus, food, every word, and then associated with images, his childhood church, childhood house, his favorite clothes, favorite pet, everything. Let's say it is N is everything, and then the probability of association with N cube, the total number required to replicate Sanjay's reasoning is N cubic number, which is too large, right? So it's but if we somehow have this number, right? If we have this number, then we can follow Sanjay's thinking with a random sampling. So let me briefly talk about the vision and language as a graph node. So you can think this as a language as a concept and vision as a sensory input, specific sensory input. So I said, oh, the animalistic thinking and human thinking is the same thing. It's a random jump, random walk in a probabilistic noisy graph. The only difference is for animals, they have only specific sensory inputs, like image, things like that, while human has a language or concept as a additional word. Concept is slightly ambiguous, so let's use language as to represent. So the word, for example, apple, and the specific images of the apple. So if we think about the language apple, the word apple is if you hear the word apple, you have some kind of blurry or abstract general image. However, there are no sensory input that matches exactly same as the word apple, right? The imaginary apple in your head, there is nothing like in the world. It's a totally separate thing. And it can mean totally different things. So it's a source of the flexible thinking. So the apple can mean apple computer or fruit apple. So however, for sensory input node, like image of apple, it is very specific instance. So there is no two same apples in the world. And there will be no confusion with the actual fruit apple and computer apple. So how this node type affects thinking. It's like if we use only sensory input node, like image node, as a thinking, then it's like you and I are watching Harry Potter movie together. Your experience and my experience are same. However, if we are using verbal node, then thinking is reading Harry Potter novel you and I, then my mental image and your mental image will be totally different, right? So that's what I mean by node type affects the thinking. So, I will skip this. So now that was the end of the theory or algorithm of the thinking. No, theory or autism story or philosophical story. So from now on, it will be more of the actually building machine, the algorithm part. So this is my proposal for building, how I say, artificial general intelligence. So there are components like auditory encoder, visual encoder, Hangul encoder. So encoder is like when you have a sensory input, it changes into the vector, right? It's a simple. You guys have done with auto encoder decoder, right? So it just changes everything into the vector, and these vectors are. This is like a FIFO, so it has a memory where first comes, first out, and in this sensory memory there is some attention. And for now, to make it simple, let's say this attention is randomly selecting out of these ones, and there is a rule matrix. This is actually matrix to make it simple. So I said attention selects one input from this sensory input, and if we multiply the sensory input and matrix, we get another vector, right? So let's say we have another vector here, and this is more like a long-term memory. So it does the dot product with the long-term memory. If you do a dot product with two vectors, it gives you one number. So based on the similarity, right? So we randomly sample one from this long-term memory based on the dot product weight. Do I make sense? Saroj, do I make sense? Yeah, let's say this is just a vector, and in the long-term memory, you are storing vectors for, let's say, apple. So this vector is apple image, let's say, and this is the image of cat. This is a sound of like mom, word mom. This is a sound of word cat. This is action of, let's say, crying. Hungry. Feeling of hungry. I don't know. I'm not sure. Okay. Anyway, so these are all vectors. You have this list of vectors, and you have one candidate vector here. It is here. And when you do a dot product between this and this, you get some number representing how similar these two vectors are, right? So if you do dot product over all things in the memory, right? You get score of similarity for each one, right? And you can select one by the probability randomly, not just choosing the maximum one. You choose one randomly based on this probability. So in that case, it will choose the Apple image vector, and this Apple image vector will become a new active node, and it will fed into the short-term memory. This is just another heap of the another heap for memory. And next time when you select something from this node, you concat those two vectors and you multiply again, gets the new vector, and things goes on. And there is a reward center here. So let me go in more detail with specific examples. Let's say this is the first learning how to speak mom, right, with the image of mom. So let's say we can say some connections are hardwired. So this is a probabilistic noisy graph. If you are satisfied, you smile or you sleep. If you are hungry, you eat or cry. If you feel pain, cry or run, right? So this is a pre-programmed. And what I mean by the pre-programmed, let's say you select a hungry vector. This one generates a vector of if I am full of the food or I'm hungry. So let's say this hungry vector is selected, and let's say this state is hungry, for example. You multiply hungry vector with the rule matrix, you get a new vector, right? This will be any random vector, but if you do dot product with this long-term memory, somehow, interestingly, the actions like eat or actions like cry gets the high scores like 0.6, 0.4, right? So if you randomly select one, you will probably choose eat or cry for your new node. That is what I mean by the pre-programmed. The encoder and rule matrix, and there are entries in the long-term memory such that when there is one node, if we multiply with the rule matrix, the next thing you get is some actions or things like that, right? This is Youngtak, do I make sense?
Is it the random selection or probability based selection? Because you
Where? So it's
eat and cry because you,
this one?
Yeah.
Yeah, so this one is random selection based on the probability. So not uniform probability. It's based on the probability.
Yeah, it can't be the random selection because if we select the random, then how can we guarantee every time it will select eat and cry when there is a hungry encoder?
Oh, so let me say random selection appears only here. Here is a selection based on the probability.
Okay. So because I heard the selection based on randomly on a long-term memory. So
no,
yeah.
This selection is based on the weight of that product.
Okay.
So Youngtak, do you?
Yeah, it's the same questions.
Same questions?
What does the rule matrix do there?
So rule matrix, let's say for now, or let's say rule matrix is given. It's just a matrix, right? So, and this rule matrix is somehow weighted such that for those simple actions like this, let's say, let's choose satisfied. So I'll go again. So hungry encoder generates satisfied or hungry vector. right? So let's say hungry vector generated satisfied vector, meaning he is full, stomach is full. So let's say here the vector is satisfied, and this one is selected as a focused input. So this, if you multiply this satisfied vector with a rule matrix, the next vector you get will be some vector that is similar to crying vector or eat action vector among here, right? So you are questioning how you can write a weight for such a thing, right? That is your question, right? So for now, because there are only few, right? The hardwired connections are only few, so it's you can easily write a simple matrix to approximate this, because the actions are not that much, right? However, if things becomes very complex, then updating rule matrix will be very challenging. If n is, let's say 10, you can somehow manually write rule matrix. However, if n is 10,000, it's difficult to build a rule matrix. So we will see how we can, adapt a rule matrix in the next slide. Any other questions? Okay, let's continue. So, first, you should think that there are only few things in the long-term memory. There is only like things like cry, eat, or learn, sleep, smile, or speak, ma, or ba, or ah. Let's say there are only very few things in the long-term memory. And if you are a baby, you cannot add all the things you see into the long-term memory, right? So the way new entry to the long-term memory is added is with the reward. So there is, in the model I showed, here is the reward center. Reward center is some kind of vending machine. So each given some specific, very specific condition, it generates a reward. So what will be these specifications, specific conditions? It's things like when you are full, right? When you are full, you are happy. So if you are hungry, then it generates a negative reward. Or if you got hugged by mom, you get some kind of reward. Sexual reward, there can be sexual reward too. What can be other reward?
For a baby?
Pardon me?
Or specific to baby?
Let's limit our scope to the baby.
Like pain, that could be the negative reward.
Yeah, pain is a negative reward.
Fear.
Fear?
Yeah.
What fear?
Some
Scary
scary dog.
Pardon me?
Dark.
The
Fear of
dark.
seeing someone.
Fear of being alone without mom.
Hearing the wind, like
So
getting
big.
scared because of the sounds and.
Yeah, sounds. I agree with fear. So there is 하루 강아지 법 무서운 줄 모른다. Yeah. So, however, so let's say this reward center is very simple, right? We cannot think that many things.
Okay.
So it's like a bending machine, or we can say it's a lizard brain. So if you know a little bit about the neuro science, human brain, let's say animals have evolved their brain, right? And around lizard, they had a reward center. So a lizard developed a reward center, and the neocortex was added on top of the lizard brain. So they say it's an old brain or lizard brain. So let's say in this case, to make simplify, mom gave the baby milk, right? So if you have something in your mouth, you feel reward. You can write it. Even if you are building actual robot, I think you will probably somehow approximate it because it's a simple rule. So whenever there is a reward, new entry is added. So new node is added. So previously there was no image of the mom node, but because there is a reward of feeding baby, new image node of mom is added here. And somehow, whenever you see a mom image, somehow you get satisfied, or somehow you get something to eat. Or whenever you cry, somehow mom image appears, right? You see there is a weak association happening here. And let's say, and whenever there is an image of mom, you also hear the sound of mom, like hi, I'm your mom, say mom, things like that. So with reward, sound of mom is associated, new node is created in here. So previously there was no image of mom. Sound of mom. But because there was a reward, this new node is created. So how this thing work? Let's say there is a auditory sound of mom, image of mom, satisfied state, and everything changes to vector once it goes through the encoder. And attention randomly selects one input here. Let's say you selected image of mom as a random focused input, and there was a reward here. So that means, add whatever is in the focused input to the long-term memory. So this thing is basically copied into this long-term memory. And now let's see the mom now this mom image vector is on the working memory, and next time randomly selected is mom sound vector, and you concat those two vectors, so mom sound vector and mom image vector, and this is the important part. With reward, rule matrix is updated such that when you multiply this vector and this matrix, the vector you get is somehow similar to the satisfied state, right? So previously it is not given automatically. I said the first rule matrix was initial value was given, but there are many random values in there. But these random values changed such that when you multiply this vector with the rule matrix, you get satisfy vector, and that was driven by the reward center. So what is happening here is basically when you have the mom sound vector, it goes into the working memory. When you have the mom, when you multiply mom sound vector, somehow you get mom image vector here, and when you multiply mom image vector with a rule matrix, somehow you get satisfy vector. So you should think this node, if we put a proof here, this is the vectors that represent these three things. Questions?
So that single vector representing all these three.
Which is single vector?
The last one, it is horizontal.
No, this one is a satisfy vector.
No, the last one which is coming from the long-term memory to
The
working
last
memory.
one,
Yeah.
this one is like what is the you are thinking? You are if this changes each changes each generates a sequence for this. So it first generates a mom sound vector, the second generates a mom image vector, third generates a satisfy vector.
Yeah, so we have three different vector for all for mom, for satisfied, and for sound.
Yeah, there are three different vectors.
But basic intuition is you're trying to do association, right? So with the satisfied vector, you're trying to associate the mom image vector and the mom audio vector.
So let's say I agree what you are saying. So basically, we are developing way of writing weight between two nodes. There is a mom sound node, mom image node, and satisfy node, and we want write the edge weight between these three nodes using this system, right? So whenever, let's say when you have the mom sound vector, if you multiply mom sound vector with the rule matrix, you get something. This is some random vector. But if you multiply, if you do dot product with things in your long-term memory, what you get is somehow you get high value for satisfied vector, 0.3, more higher vector for the mom image vector, and low value for like a cry vector, low value for something like that, right? So this rule matrix somehow captures the weight, association weight among the node.
And how is the focus memory chosen from the working memory?
Is it 3? What time is it now?
220.
2:20. Okay. I think we will probably stop here. Not stop here. I mean, we will not go any more slide now. So, can you say your question again?
How is the focus memory chosen from the working memory?
So for working memory, so I can say to make things simple, randomly selected. That is one option, but somehow I feels like there is this component is learned. Yeah, it's like when you are driving, before you learn how to drive, stop sign doesn't have a meaning to you. But when you learn how to drive, begins to attend to the stop signs. So there are some kind of learned component here. Let's see. Okay, so I think these values, yellow things are probably learned component. Blue things are innate component, meaning it is given. So the encoders are also given. There is no training on the encoder. In terms of the deep learning, we can say we just use the ImageNet best classifier, like any model, like VGG model, VGG encoder as an encoder. So we do not do training on the encoder part. So encoder is also innate. So that is the probably how we train. There might be some training on the focus for this part. Any more questions?
So the reward center, when you say it's given, that means that would be manual input rewarding, or?
Manually written. So it's like how I express it. So it's like a vending machine or lizard brain. So I, as a developer of artificial general intelligence, I will write it down manually, right? So there are some conditions that will generate a reward, and there are not so many. I asked you guys when the babies will get reward, then there are not so many, right? You guys thought about it. So it's like if you get coin, and the user select a button, give him like a Pepsi or Sprite or things like that. It's that kind of simple logic. If you get fed, then generate dopamine that makes you happy. If you are warm, generate a reward. So there are not so many things that has to be written. So I will manually write this part, but I cannot write the rule matrix manually.
At the first time, usually there are no memories in the long-term memory.
At the beginning, there is something. Even at the beginning. So even at the birth, it's like things like cry or move left arm, move right arm. What will it be? Close eye, open mouth, eat, suck. Something is already, and things like, yeah, those are already in the long-term memory. Okay, guys, we will continue next week. So
Can we get the slides like till today, whatever?
yeah, I'll share the slide. Okay. Mm-hmm.
See you.
See you.